Night chemistry. Physical marvels of H2O. Welcome, midnight traveler, to night chemistry, the starlit observatory where matter itself reveals its secret choreography. Tonight the stage is a frozen bay bathed in lunar glow. Ridge-backed glaciers loom like alabaster cathedrals. A thin mist drifts between their spires, shimmering with faint auroras. Each creak of ice, each distant rumble, reminds us that water is never truly still. It stretches, bends, and reinvents itself in realms most eyes never see, transforming from feather-light flakes to crystals dense as marble, from glass-smooth lakes to exploding cavitation bubbles hotter than starlight. For the next hour you will glide through this hidden gallery of forms, 25 and more phases of ice stacked like exotic postage stamps, a rare electric crystal that hums with piezoelectric charge, a quiet density trick that lets entire lakes survive winter, and bubble implosions so fierce they carve metal and light their own blue sparks. All of it unfolds in the hush between heartbeats, carried by a tide of steady 60-beat surf and gentle narration designed to guide you into calm. Allow curiosity to linger, but let urgency dissolve like frost under dawn. The journey begins among moonlit ridges and ends in a mirror-still lagoon of dreams. Step forward, the ice will hold, settling into crystal calm. Find a comfortable position, sitting or lying, so your spine feels as tall and effortless as a fir tree dusted with fresh snow. Let your shoulders sink by the width of one breath. Let your jaw unclench as though exhaling a puff of winter air. Close your eyes or soften your gaze until the room blurs into quiet shadow. Tidal breathing. 1. Inhale through the nose to a slow count of 4. 1, 2, 3, 4. Drawing in air that feels crisp as alpine morning. 2. Hold for another 4. Steady, weightless. Imagining that breath freezing momentarily into a perfect hexagonal flake that floats within your chest. 3. Exhale for 6. 1, 2, 3, 4, 5, 6. Allowing the flake to sublimate into clear vapor, carrying worries away like fog dissolving at sunrise. Repeat 2 more cycles at your own tempo. With each exhale, picture an ice crystal growing outward, branch by branch, until its lacework fills the darkness behind your eyelids, then melting cleanly, leaving only stillness. Now summon the image of a single snowflake drifting through moonlight. Follow its slow descent, past silent peaks, past a frozen lake sealed in midnight blue, down to the surface where it lands without a sound. The flake lingers, then merges into the sheet of ice, adding one invisible layer to a structure that has grown all winter long. Beneath that sheet a pocket of liquid water remains, warmer than the air above, stirring gently like a faint heartbeat. Let yourself sink through the ice, entering that sheltered space. The ceiling above glows with trapped starlight. Below, the lake bed is cloaked in velvet dark. Everything is hushed, buoyant, expectant. Feel the water cradle you, even if you're lying on a couch, and know that pressure and temperature weave protective spells in places no sunlight reaches. Take 1 more breath in for 4, hold for 4, and release for 6. Muscles loosen further. Thoughts drift like snowflakes settling on silent fields. The bay, the glacier, the hidden lake all wait to reveal their marvels. When the next inhale arrives, you will be ready to witness how water turns itself to crystal music, electric stone, and dancing light. The exploration begins. Gallery of 25 frozen faces. Moonlight brushes the glacier walls like powdered sugar, but every shimmering ridge hides a secret staircase of forms the droplet can climb. Long ago we thought ice had only one face, the delicate hexagon that falls from winter clouds. Then, in 1912, a young American named Percy Bridgman built a steel press the size of a piano and began squeezing water between anvils. He watched the clear crystal shiver, rearrange, and settle into something harder, denser, utterly new. Each click of his pressure gauge became a passport stamp, admitting science to a land where temperature and force sketch unfamiliar alphabets. Start with the ice that blankets your driveway after a night of frost. Chemists call it ice 1H for hexagonal. Touch it in thin flakes and it sings under your fingers. Crack a thick slab and it groans like an old door. Stack the molecules into perfect cubes instead of hexagons and you get ice 1C, a form that hides in high clouds. Its crystals bend sunlight into halos so faint most eyes miss them. Yet pilots crossing the Arctic sometimes glimpse white rings wrapped around the sun like ghostly bracelets. Turn the pressure up a little, as Bridgman did, and ice 2 appears. Denser with layers offset like shuffled playing cards. Raise the squeeze again and you reach ice 3, then ice 5, then ice 6, each step shuffling molecules into new patterns. Imagine a time-lapse film. Rows of oxygen atoms sliding, tilting, clicking into alignment while hydrogen bonds flip like weather vanes in a storm. At 8,000 atmospheres, more weight than 10 Grand Canyons piled on a single coin, ice 7 forms, so tightly packed that its oxygen framework resembles a honeycomb hammered flat. Diamonds would crack long before ice 7 submits. Pause to breathe. Draw in cold night air for a slow count of 4. Hold that breath, picturing layers of ice sliding into place. Release for 6, letting tension drip away like meltwater trickling down a crevasse. Beyond ice 7 lies a border of physics and poetry. Inside diamond anvil cells scarcely wider than a fingernail, researchers at the European synchrotron fire laser pulses and push pressure past 1 million atmospheres. Molecules lock into ice 8, ice 10, finally ice 11, each structure stranger than the last, with hydrogens ordered like marching lanterns in a festival of silence. At this depth hydrogen bonds straighten until protons perch midway between oxygens, as if unable to decide whose house to visit. Some call the result superionic ice. Oxygen atoms frozen in place while protons wander free, turning the solid into a pallid conductor. Planetary scientists believe such phases churn inside Neptune and Uranus, their restless protons helping twist magnetic fields so lopsided they baffle textbooks. Return to Earth and lower the pressure, but slide the thermometer far below refrigerator cold. Near 200 degrees below zero, ordinary hexagonal ice quietly transforms into ice 11, an electrically ordered version of itself. Every proton tilts the same way, giving the crystal a permanent polarity. Set 2 slivers together and they will attract like tiny batteries, crackling faintly if a needle probes them. Because ice 11 forms only in the purest, driest corners of Antarctica, its discovery arrived late. Snow cores drilled in the 1990s revealed thin horizons of this electric frost, whispering tales of ancient cold snaps when clouds carried almost no dust or salt to disturb proton discipline. Now warm the sample to just below 0 degrees Celsius and watch a miracle of kindness unfold. Most substances grow steadily denser as they cool, but water halts its contraction at 4 degrees, then reverses. Lakes therefore chill from the top down. Ice floats. Fish survive winter beneath an insulating roof. In 1805, Scottish professor John Hope packed equal tubes of water and quicksilver, noting that the mercury solidified first even though it usually freezes lower. He guessed correctly. That water's hidden density trick counters the matchmaking of frost. Picture a pond at night in early winter. Surface crystals link arms, expand and push downward, but denser 4-degree water settles to the muddy bottom, shielding carp that glide in slow circles half awake. Take another breath. Feel the cooler air at the tip of your nose and recognize the same density dance happening in sinus passages, where exhaled moisture condenses, warms, and rises again. Move now to the realm of violent delicacy. Cavitation. Fill a beaker with water and spin a propeller fast enough, and pressure behind each blade drops so sharply that vapor bubbles bloom, then collapse in microseconds. Lord Rayleigh first mapped the force of these implosions in 1917, suspecting they might pit battleship screws. A century later, researchers at Stanford designed a silicon cavitator, no larger than a postage stamp, that funnels water into slits thinner than a hair. As bubbles implode, they flash white-blue, reach temperatures hotter than molten steel, and fire shock waves strong enough to pierce aluminum foil. Engineers hope these tiny collapses will one day disinfect medical instruments or drive compact rocket pumps. Yet in your glass of sparkling water, the same physics pops each bubble, releasing miniature puffs of sound too soft for waking ears. Higher up the glacier, something gentler happens. Under the weight of its own frozen mass, ice near the base melts ever so slightly, pressure lowering the melting point by a fraction of a degree, then refreezes a few centimeters away. This regelation lets glaciers flow like slow syrup, bending around mountain shoulders, smoothing granite into striated mirrors. In 1849, Michael Faraday sprinkled iron filings onto 2 ice cubes, pressed them together, and watched them weld into one block upon melting and refreezing along the filings' paths. The same practice lets ice climbers plant metal screws that grip the wall as meltwater freezes around their threads, creating anchors firm enough to hold a dangling human over a void. Deeper within the glacier, at pressures too mild for exotic phases yet too high for brittle fracture, ice behaves like warm taffy. Crystal grains slide past one another, guided by rulebooks written in proton language. These slow currents entrain dusty layers, arching them into sinuous bands that record volcanic winters, forest summers, desert winds. A single borehole through Greenland ice reads like a mile-long diary. Cinnamon stripes laden with Saharan dust, gray threads of ash from Krakatoa, lead-white ribbons marking industrial smog. Each layer is a slide in water's ever-expanding gallery. Finally, return to the present shoreline. The glacier walls no longer feel monolithic. They pulse with hidden halls where molecules rearrange on rising thermodynamic staircases. High overhead, the moon touches a peak, its reflected beam splitting into faint colors where a layer of cubic ice drifts like luminous smoke. The cold air tastes metallic, hinting at ions trapped in electric ice far below. Beneath your imaginary feet, the lake murmurs, adjusting density with each passing minute, holding warmer water close to mud and keeping the underworld alive. Breathe in for 4, hold, breathe out for 6. As your breath leaves, imagine it condensing into fog, freezing into diamond dust, sinking onto the glacier to become one more molecule in the endless masquerade. Nothing in the droplet is ever wasted. Every phase is a costume for a different stage. And as you settle deeper into calm, remember that even now a proton somewhere inside your own cells may tunnel through a hydrogen bond, rehearsing the next act in water's relentless play of forms. Let the thought dissolve like frost beneath a rising sun. The crystal gallery stands revealed. Its doors remain open in darkness and in dreaming alike. Ice 11. The electric crystal. Arrive with the hush of polar night. A katabatic wind sighs across Antarctica's high plateau, sculpting drifts that glint under a low, pale moon. Temperatures hover near 200 degrees below zero, so cold that the usual jostle of water molecules slows to an almost musical stillness. In this rare, quiet, ordinary hexagonal ice rearranges itself into a form both delicate and charged. Ice 11. Imagine a single crystal grain buried 100 meters down, pressed flat as a playing card by millennia of snowfall. At higher temperatures, its protons spin and flutter, never choosing one orientation for long. But as the deep winter of space settles over the plateau, thermal energy ebbs. One by one, the protons stop shuffling and face the same direction, like weather vanes clicking into alignment after a squall. A subtle current trickles through the lattice, too faint to light a lamp, yet enough to give the entire crystal a permanent polarity. Beneath your mind's eye, north and south surfaces emerge where none existed before, and the ice hums with piezoelectric potential. Breathe slowly. Draw 4 counts of air so crisp it seems to crackle. Hold the breath and feel a thin filament of charge stretching the length of your spine. Release for 6 counts, letting that filament relax into a mild glow. The first hints of this electric frost reach science not through microscopes but through anomalies. In the 1980s, glaciologists drilling cores near Vostok Station recorded unexpected voltage spikes whenever a section of ancient, ultrapure ice passed their electrodes. Physical chemist Satoshi Kawada, intrigued, flash-chilled laboratory ice below -180 degrees Celsius, doped it lightly with potassium hydroxide to coax proton order, and found that the sample flipped the needle of his electrometer without a spark. Under polarized light, the crystal flashed blue-green, revealing domains like stained glass windows, each pane an area where dipoles marched in lockstep. When he pressed on the sample with a sapphire pin, a measurable current rippled through the circuit board, proof of spontaneous piezoelectricity. Picture Kawada's lab. Glass dewars hissing with liquid nitrogen, a single red light casting its glow over frost-dusted wires, the only sound a soft ping as thermal stress fractures a clamp. A fragment of ice 11 lies on insulating quartz, no bigger than a grain of rice, yet internally arranged with stricter discipline than any regiment. Touch one face with a gold needle and the opposite face responds. Remove the pressure and the charge vanishes like breath on glass. Ferroelectricity in water ice seems almost whimsical. Protons, after all, are the lightest dancers in nature's ballroom, yet it carries deep implications. In Saturn's rings, countless house-sized boulders of ultra-clean ice spin in darkness 30 degrees above absolute zero. Astronomers model collisions there and find that electrostatic forces, not merely gravity, help grains clump, rebound, or tear apart. Electric alignments could even influence how ring arcs sort themselves into sharp, braided filaments seen by the Cassini probe. Farther out, on Kuiper belt objects where sunshine is dimmer than moonlight on Earth, Ice 11 may coat entire hillsides, its charged surface dusting itself with organic aerosols drawn in by electrostatic zest. Closer to home, lake ice seldom becomes 11 because salts and dust scramble proton order. Yet pockets form in places pure as distilled water. High-altitude cirrus where vapors freeze in isolation, cavities within diamond-like inclusions of glacial ice, even microscopic cracks inside ancient stalagmites fed by drip water filtered through limestone. Each enclave might store a whisper of potential energy, waiting for the faint rumble of tectonic stress to release a pulse that travels faster than any seismic P-wave, an electrostatic foreshock perhaps of distant quakes. Let your breath deepen. Inhale for 4, hold for 4, and sense protons settling into tidy ranks across the mind's horizon. Exhale for 6, and imagine the ranks glowing softer, content to wait. Engineers have begun to wonder, could Ice 11 be harvested for sensors in the outer solar system? Tiny pressure gauges that need no batteries, powered by the squeeze of alien winds. A wafer of ordered ice, 10 microns thick, mounted on a graphene membrane, might register acoustic vibrations in Neptune's stratosphere, translating each gust into a flicker of voltage that radar can read across 50,000 kilometers. Laboratory prototypes already detect footfalls of ants walking on glass, the piezoelectric response amplified by a swirl of potassium ions frozen in place. Challenges remain. Finding a way to grow defect-free sheets at scale, preventing sublimation. Yet funding quietly trickles in from space agencies who imagine entire weather stations printed in ice, dropped onto comets to sing currents of crystalline data back to Earth. Return now to the Antarctic plateau. A drilling rig groans, raising a transparent cylinder of snow-blue ice older than humanity's written memory. The core catcher opens. Technicians lift a rod glowing faintly under polarized headlamps. Lines of trapped bubbles cross the sample like Morse code. Among them, a sparkle of proton-ordered domains catches the light, each domain a frozen voltmeter of past climate. When summer scientists later split the core with a diamond blade and run electrodes along its face, spikes appear precisely where global dust content once dipped near zero, revealing windows of unmatched atmospheric purity. Records reconstruct nights long before instruments, telling how volcanic winters cleansed the air, how cosmic dust ebbed, how magnetic reversals may have scrubbed odd isotopes from the sky. Science learns, and storytellers listen. Beneath the drone of lab freezers, a quieter truth emerges. Water is willing to keep accounts of its journey. Its protons realign, store charge, release it under fingertip pressure, and freeze again to wait another age. No need for ink or film. The molecule itself is notepad, archive, and radiator of faint electric sighs. Feel your pulse. Each throb sends a pressure wave through blood, another fluid rich with protons. Cell membranes exploit that wave, pumping ions to write impulses racing toward memory and dream. Even now, ice she's discipline echoes in your neurons, modest but steadfast. Ordered orientation enabling signal. Disarray bringing rest. The symmetry between nerve and glacier feels as surprising as snow in summer. Yet it is there, quiet as patience. Exhale fully. Picture electric crystals sliding beneath the South Pole. So cold they sing in vibrations too low for ears. Above them the aurora curls green and violet, driven by charged storms on the sun. Storms that remind us electricity courses through vacuum as readily as through ice. With the next inhale, let go of icy laboratories and planetary rings. Hold. Exhale, and watch frost on the mind's window fade to clear pain. Ice 11 retreats into darkness. Its protons once more content to wait, tiny compass needles frozen northward until the planet warms and reclaims its charge. The path ahead leads from crystal electricity to gentler wonders of density. Ponds that refuse to freeze solid, creatures saved by an accident of physics at 4 degrees. For now, rest in the lingering tingle along the skin, as if a cold spark flew from glacier to fingertip and settled into calm. And the moon above the plateau keeps shining, its light sweeping across thousands of square kilometers of proton-ordered snow, a hidden circuit glowing under the quietest sky on Earth. The 4-degree miracle. A pale wash of dawn blue glimmers on the glacier rim, but the hidden lake beneath its ice ceiling remains steeped in midnight calm. Here, in the sheltered water between rock and frost, the next marvel unfolds. A simple curve on a graph that saves forests, salmon, and perhaps the story of life itself. Water, alone among common liquids, grows less dense as it chills below 4 degrees Celsius. That modest quirk, barely a percent, holds continents steady through winter, guides ocean currents, and hums inside thermostats that steady your home. Tonight we drift through its quiet arithmetic, from Scottish lecture halls to alpine ponds, from subterranean ice caves to skyscraper chillers that levy rent on hot summer nights. Candle, 2 thermometers, and a question. Picture Edinburgh, January 1805. Frost feathers every window in the lecture theatre of John Leslie's natural philosophy class, but across campus another professor, John Hope, prepares an experiment of greater elegance. On his oak bench stand 2 identical glass cylinders, each as tall as a child's arm. One is filled with mercury, shining like pooled moonlight. The other holds Edinburgh pump water, faintly green from kelp ash soap. Hope lowers a wax-sealed thermometer midway into each column, then slides a second thermometer into the very bottom. Students shuffle closer, their breath fogging spectacles. Hope drops snow into both jars until surfaces crust with ice. Minutes pass. The mercury's lower thermometer leaps ahead, minus 30 degrees and falling, solid metal contracting as expected. In the water jar, however, the bottom sensor settles not at 0, but curiously rises, hovering near 4 degrees Celsius even as the column above begins to freeze. Hope repeats the test by candlelight for weeks, convinced no trickery remains. Results hold. Water reaches its densest point 4 degrees above freezing, then inexplicably expands. Hope's finding travels quietly through Royal Society notes, overshadowed by more bombastic news of galvanic batteries and hydrogen balloons. Yet engineers soon notice their mills work through winter because river bottoms stay liquid. Merchants realize fish ponds seldom freeze solid. Botanists observe that tree roots survive blizzards snug in soil pockets warmed by thermal inversion. Pause and draw a breath. 4 heartbeats in, hold briefly, then exhale for 6. Feel coolness gather along your collarbone. sinking like chilled water toward an imaginary lakebed where living roots wait out the cold. Molecular acrobatics beneath a graph. Why this inversion? Return to the droplets microballroom. At warmer temperatures, molecules jitter freely, sliding closer as heat slips away. But dip below 4 degrees and hydrogen bonds stiffen into wider angles. Small hexagonal rings stretch outward, forcing molecules into a lattice that occupies more space. Imagine dancers suddenly extending arms and locking elbows, widening their circle just when the floor grows most crowded. The ensemble now floats slightly higher in the punch bowl, pushing colder water upward. When the circle chills at 0 degrees, one final expansion crystals into ice so light it crowns every glass. Add salt, and the plot bends. A saline ocean reaches its density peak closer to -2, the temperature at which brine begins to freeze. Antarctic bottom water, born as salt is rejected from sea ice, plunges down continental shelves and crawls along abyssal plains like a dense slow river, ferrying oxygen thousands of kilometers before mixing with warmer layers. Without the 4-degree quirk, shifted for salinity, global overturning might stall, starving deep sea life and leaving equatorial surface waters boiling beneath unchecked sun. A winter lake in cross-section. Visualize a small kettle lake in northern Finland at sunset mid-January. Ice a dozen centimeters thick plates the surface, etched by skaters' blades now buried in drifting snow. Beneath the lid, a narrow stratum of 0-degree water hugs the ice. Just below rests denser 4-degree water, blanketing benthic mud like a woolen quilt. Copepods, snails, and torpid pike linger where darkness and comparative warmth meet. At night, the zircon luminescence of the aurora trembles through ice, but below, life waits unhurried. Come spring, sunlight thaws surface ice. Wind rakes the lake, overturning the column. Nutrients that settled through winter swirl upward, igniting plankton blooms that feed larvae and waterfowl. Entire food webs hinge on that inversion. Strip it away. Suppose water behaved like ethanol, densest at 0 and steady thereafter, and lakes would freeze from bottom to sky. Each thaw would demand weeks of solar input to melt vertical ice prisons. Fish gills would find only crystal, not current. Hold another breath. Picture the warmth cupped inside a quiet pool, the cold crowding above. Release, letting the gentlest exhale ripple across that imagined waterline. Architecture of warmth and quiet refrigerators. The density trick not only shelters minnows, it cools skyscrapers. Inside, many glass towers hum vast chilled water loops. At night, electric chillers run while grid tariffs dip, driving water to just above freezing and packing it into insulated tanks. During the day, warm air from office floors circulates through air handlers, kisses chilled pipes, then returns refreshed, sparing the building peak hour electricity. Engineers tune brine concentration so fluid remains densest at its nighttime set point, limiting stratification that would otherwise require heavy pumps. Each dollar saved at noon rides invisible on water's 4-degree pivot. Similarly, thermal reservoirs and solar thermal plants exploit stratification. 85-degree molten salts sink beneath 250-degree counterparts until valves mix them through turbines at dusk. Those salts, not water, hold the heat. Designers borrowed the principle from alpine lakes where layers seldom mingle. The puzzling story of the fjord that refused to freeze. Travel west to Norway's Narvik Fjord, latitude above the Arctic Circle, yet free of sea ice most years. Warm Atlantic currents explain part, but local fishermen recall a winter when air temperatures plummeted to -30 and still the fjord only glazed at sheltered coves. Oceanographers drilled through the thin skin and found 4-degree water welling from submarine springs, denser than brackish surface flow. It rose just high enough to lift colder brine, flipped, cooled, sank again, a slow convection cell powered by the density anomaly. The fjord functioned like a natural heat pump, sparing docks and fishing stakes the crush of pack ice that wrecked neighboring bays. Scientists proposed a similar system to keep harbors ice-free. Inject lake-bottom water through up-facing diffusers near piers. Pilot tests at Duluth Harbor show promise. A trickle of 4-degree water blooms into convection, ferrying latent heat upward and saving dredging crews weeks of icebreak operations. Density as historical dial. Climate detectives wield the anomaly to extract ancient temperatures from varved lake sediments. Each lamination, light summer silt, dark winter clay, bears clues in trapped microfossils. But whether the bottom froze influences which diatoms appear. In cold years when dense 4-degree water failed to form a stable cushion, ice scoured clay and oxygenated iron layers. Counting such scours in Scandinavian varves reconstructs medieval climate swings, mapping harvest booms and Viking voyages to decades of stable stratification. On a finer scale, freeze frames inside stalagmites tell local tales. When cave drip water cooled below 4 degrees en route through limestone fractures, calcite precipitated distinct from warmer seasons, etching density lines scientists decode with lasers. Thus water's anomaly becomes not just guardian of modern lakes but historian of Pleistocene floods, logging whispers in crystal diaries. Molecular simulations and quantum teas. For over a century textbooks called the anomaly unique, yet in 2024 researchers at Sorbonne fed a quantum-corrected potential into massive supercomputer runs and reproduced the density curve precisely. Visualizations showed transient 5-molecule rings forming miniature dodecahedra that open and close like breathing lungs when temperature nudges them below 4 degrees. Each ring traps a pocket of void, expanding volume without mass. Such insights refine climate models. Cloud microphysics, snowfall density, even sound speed in polar ice caps, handy for neutrino telescopes, depend on water's delicate balance of voids and hydrogen locks. While electrons hum inside those bonds, proton tunneling glides beneath. At near-zero temperatures, 2 positions for a hydrogen become one blur, further encouraging the lattice to adopt its spacious stance. Thus quantum mechanics, not classical intuition, crowns the anomaly king. Breathing with the lake. Let imagination return to that Finnish kettle. Lower yourself onto the frozen surface, ear pressed against blue ice. Hear far below a soft tick, thermal contraction cracking the shell, followed by a hollow boom as shock waves race outward. These cryoseisms, or frost quakes, punctuate nights when surface temperatures drop faster than water can surrender heat. Yet beneath the uproar the 4-degree layer holds steady, a warm lung inhaling, exhaling, equalizing fracture lines. Inhale now for 4. Count snowflakes descending through headlamp beams. Hold 4. Feel them settle on your jacket. Exhale 6. Let tiny crystals slide into furrows, then soften into beads. The same cycle repeats within every northern lake, within ocean mixed layers, within your coffee cup warming hands by winter windows. A gentle exit. Far above, dawn finally brushes glacier summits in pale saffron. The hidden lake murmurs anew. Density gradients begin to shuffle under early light. Trout stir, enticed by oxygen streamed downward overnight. Soon the first gull will scream across crystalline silence, and a pine cone drop ripples the margin, drawing ring upon ring until damp moss silences motion. For now, remain at the threshold between sleep and waking, buoyed by the physics that lifts ice to the top and tucks warmth beneath. Know that whether you rest beside an equatorial lagoon or in a rooftop loft, the same 4-degree miracle moderates your world. Easing climate swings, cradling embryos in amniotic seas, and penciling faint memory lines in the sediments of time. One more breath, in, suspend, out, and let the miracle settle like silt on the lakebed. Ahead waits a realm of restless bubbles, where collapsing caverns of vapor flash hotter than a forge. But this pause belongs to quiet density, to the idea that sometimes becoming lighter is a heavy responsibility borne gracefully by a humble molecule. Sleep, if you wish, upon that thought, water holding warmth, life holding possibility, until curiosity calls again. Cavitation, where bubbles fold light and steel. Imagine kneeling beside a moonlit stream, palm cupped beneath the surface. A thin film of water slips between your fingers, smooth as silk. Yet hidden within even this gentle flow lies a force fierce enough to carve bronze propellers and flash like distant galaxies. Tonight we drift into that secret frontier where liquid tears itself apart, vapor bubbles bloom, and in the blink of an eye, collapse with the heat of a small star. This is cavitation. Silent at first glance, astonishing when heard with instruments tuned to the heartbeat of water. The birth of a void. Begin with a simple propeller turning in river water. As each blade swings forward, pressure on its rear side plummets. If the drop is sudden enough, liquid can no longer hold itself together. Pockets of vapor appear like tiny, perfect balloons. They are not filled with air but with the very vapor of water, created by a local boiling event at temperatures far below a kettle's whistle. For a split second these balloons drift in the wake, seeming harmless, delicate soap spheres that shimmer and vanish. But the vanish is no gentle fade. When the blade passes, pressure returns, and every bubble implodes at nearly the speed of sound. Walls rush inward from all sides, focusing energy the way a magnifying glass focuses sunlight. At the instant of collapse, a microjet, a needle of liquid less than a hair across, lances through the bubble's center at hundreds of meters per second, piercing nearby surfaces with pinpoint ferocity. Accompanying that jet, temperatures soar tens of thousands of degrees, pressures spike thousands of atmospheres, and a brief flash of blue-white light called sonoluminescence flares into being. Hold a soft inhale for 4 counts. Imagine that microjet as a silver dart frozen in mid-flight. Release for 6 counts. The dart melts back into darkness, but not before scarring metal hulls and polishing river stones smooth as bone. Lord Rayleigh's first whisper. The earliest mind to chase this violent whisper was John William Strutt, better known as Lord Rayleigh, who in 1917 posed a seemingly modest question: how fast can an empty cavity disappear in an infinite liquid? With pencil, slide rule, and extraordinary intuition, he derived an equation predicting the energy released when a bubble vanishes. His calculation featured variables for radius, pressure difference, and density. Simple terms that, combined, foretold forces capable of shredding steel. When the Royal Navy later noticed propeller blades pitted like the surface of the moon, Rayleigh's math offered the culprit: invisible bubbles born of their own motion. Engineers responded by enlarging blade area, smoothing edges, coating surfaces with nickel aluminum bronze. Yet cavitation remained stubborn, gnawing on torpedo fins and river turbines alike. The unseen, it seemed, delighted in defying armor, from destruction to delicate tools. Decades passed before researchers began to ask whether that destructive pinch could be tamed. High-speed cameras in the 1950s captured collapses at up to 100,000 frames per second. Grainy footage revealing a single luminous pulse just before bubbles died. By the 1990s, laboratories at the École Polytechnique and UCLA used laser pulses to seed micron-sized voids in water, collapsing them near glass slides to cut microscopic channels. Surgeons imagined scalpel-thin jets, ablating cataract-clouded lenses while sparing fragile retinal tissue. Even pottery felt the touch. Ultrasonic cleaners harnessed cavitation to shake dirt from jewelers' filigree and strip oil from diesel injectors. Millions of bubbles collapsing in concert form an invisible scrub brush that reaches corners bristles never could. The same principle now washes semiconductor wafers, ensuring nanoscale circuits form in pristine silence. The Stanford Cavitator, 2024's shimmering disk. In 2024, a team at Stanford University unveiled the Silicon Cavitator, a flat disk no larger than a coin but etched with concentric spiral channels only 4 microns wide. Water enters at the center, whirls outward, and, guided by carefully tuned pressure drops, spawns uniform rows of vapor cavities. Embedded fiber optic probes detect the faint blue sparks of sonoluminescence marking each collapse, while piezoelectric films harvest the resulting shock waves as electrical pulses. The device achieves three marvels at once. 1. Precision. Bubbles form where engineers choose, collapsing within nanoseconds of one another, their microjets aimed like archers. 2. Energy recovery. Each implosion generates a mini-quake. Layered piezo films translate vibration into microwatts of power, enough to run sensors that log temperature and flow. 3. Sterilization. Shock waves rupture bacterial membranes, allowing sterile water loops in medical devices without chlorine or boiling. Picture the cavitator beneath a microscope. A midnight disk lit by scattered laser specks, bubble rings blooming and vanishing like galaxies in time-lapse. Every event is silent to the naked ear yet roars inside the silicon, captured by nanometer shivers and fed as trickles of voltage to blinking LEDs. A constellation in miniature. Pause for another breath. Draw in the hush of your room as though inhaling starlight through those spiral channels. Hold. Release, sending any tension down the whirlpool until it collapses into calm. Sonoluminescence. Light from a dark place. Years earlier, physicists at the University of Illinois trapped a single bubble in an acoustic standing wave. With each oscillation, the bubble grew and shrank, finally collapsing with a flash so sharp that even photomultiplier tubes struggled to mark its lifespan. Spectra hinted at temperatures surpassing 10,000 Kelvin, hotter than the sun's surface, inside a cavity smaller than a red blood cell. The bubble re-inflated in the next acoustic cycle and flashed again, repeating up to 20,000 times per second, a pulsar made of vapor and sound. What exactly turns implosion into light? Theories range from Bremsstrahlung radiation of plasma electrons to collisions of excited oxygen and hydrogen radicals. Yet mystery persists, protected by scales too swift and too small for direct probe. One experiment replaced water with deuterated heavy water, hoping fusion glow might peek out. None was seen, but curiosity only deepened. Even unanswered, the phenomenon teaches how pressure concentrates energy, how void and substance dance. Crafting bubble lenses and microneedles. Modern applications read like science fiction delivered gently. A microscalpels that cavitate near bone, carving cochlear windows finer than drills can manage, leaving hearing intact. A drug delivery bubbles coated in lipids, injected into bloodstream, then burst by focused ultrasound at tumors, opening pores for chemotherapy with pinpoint delicacy. Underwater jet engines leveraging a cavitating supercavity to envelop projectiles in vapor so they glide through sea almost as through air. The Shkval torpedo's secret born in Soviet labs, now refined at MIT for rescue drones. Yet every advance pays homage to the first observation. The bubble is both friend and foe, gentle when guided, ruthless when ignored. Shipbuilders still design propeller tips to avoid vacuum pockets. Hydroelectric dams still monitor turbines for cavitation chatter that foretells corrosion. The line between polish and ruin is measured in microseconds and microns. Listening to tomorrow's caverns. In a dim room at ETH Zurich, doctoral students set quartz sensors against a titanium cavitation tunnel. They sit silently, headphones off, letting software translate pressure waves into colors on a screen, blues for gentle hum, reds for violent collapses. By dawn they will adjust chamber shape by a single millimeter, reducing red by half. Efficiency up where down. Ships will sail farther, hydropower will hum softer, and the water will keep its explosive secrets beneath thresholds of human hearing. Take a final slow inhale. Envision one luminous bubble shining teal, shrinking faster than thought, then winking out. Energy focused, released, gone. Exhale for 6, letting that spark echo across your mind, then fade to shadow. Quiet wake. The stream beside you, once so innocent, now glows with unseen possibility. Each eddy might foster cavitation, sculpting pebbles into ovals over decades. Each fall of water over stone could flash with sonoluminescent fireflies too swift for eyesight. Yet the world remained serene, for water guards its heat behind veils of vapor and brevity. Let the knowledge settle like silt. Propellers turn, carrying dreams across oceans. Silicon discs hum under hospital benches, cleansing fluid paths. Somewhere a fusion researcher watches for blue hints in collapsing heavy water spheres. And you, listening, can rest assured that even the fiercest energies in nature may cradle stillness when balanced within patient design. Breathe one more time. The bubbles are distant now. Collapses soften to memory. Ahead waits a realm of moving glaciers and regelation flows, but for this moment only hush remains. The hush left after water folds light and steel, then drifts back into quiet liquid night. Ice sculptors in motion. Night stretches a velvet shawl over the glacier's back, yet beneath the hush, the ice is moving, slowly, patiently, with purpose. From a distance the frozen river looks rigid as granite, but draw closer, and you feel a faint pulse, a rhythm older than language. Tonight we slip inside that rhythm, tracing how pressure melts crystalline bonds, how regelation welds broken edges, how glaciers flow like syrup made of cold blue stone, and how even within those stones, protons keep gliding through quantum tunnels. At the glacier's head, snowfall compacts layer upon layer, each flake rearranging into firn, then ice, then something denser still. Under its own weight, the ice bed deepens until it grips a mountainside valley like a hand inside a velvet glove. Gravity pulls downhill, but friction holds. Somewhere between pull and grip, a thin film of meltwater appears, born not from sunshine but from pressure melting. Squeeze any ice hard enough and its melting point falls a hair below zero. Release the squeeze and it refreezes. That quirk greases the glacier's soul, creating a sliding surface no thicker than a sheet of paper. Imagine yourself standing on a midnight ledge, headlamp off. You hear no roar, only an almost subliminal groan, like timber settling in a centuries-old church. That is basal slip, the glacier's belly gliding over pulverized rock, polishing boulders into striated mirrors that will one day stud museum halls as glacial pavements. Each millimeter of motion takes hours, sometimes days. Yet given decades, the ice river may travel from alpine shelf to forested foothill in silent triumph. Pause for a breath. 4 counts in, hold softly, 6 counts out. Picture that breath condensing, freezing, then slipping under a granite arch the way meltwater threads beneath the glacier. Regelation, the needle and thread of frozen fabric. Far up valley, a sliver of rock juts into the glacier's path. Ice presses on the upstream face, lowering its melting point by a fraction of a degree, just enough for a whisper of water to form. That thin film creeps around the obstruction, re-encounters lower pressure on the downstream side, refreezes, and locks the rock deeper into its frozen vise. This melt-flow-refreeze cycle, regelation, is the glacier's seamstress, stitching around pebbles, tree trunks and cliff edges, smoothing them into streamlined roche-moutonné cliffs. The same principle helps ice climbers anchor screws into waterfall columns. When steel threads bite into the wall, local pressure melts a hairline ring. The moment tension eases, the ring freezes, bonding metal to ice with a grip strong enough to arrest a falling alpinist. Even delicate ice chandeliers, those transparent stalactites dangling in winter caves, rely on regelation at their tips. Water spreads over an emerging crystal, freezes, lengthens the spire by a breath, then melts anew to repeat. The quantum murmur inside Ice 8. Descend deeper, past the brittle crust, past ductile blue layers streaked with airborne dust, into zones where pressure multiplies, and ice transforms yet again, not by macroscopic flow but by atomic sleight of hand. At a few thousand atmospheres, hexagonal symmetry yields to more compact arrangements. Ice 6, Ice 7, and finally Ice 8, a dense phase where oxygen atoms line up in interlocking cages. At this depth, where overburdened pressure would crush submarines into porcelain shards, classical vibration all but ceases. Yet proton motion persists through quantum tunneling. A proton slips through an energy barrier instead of climbing it, appearing on the other side in the blink of nothing. Laboratory physicists chill ice-8 in diamond anvil cells and shoot neutron beams through the sample. Scattered patterns arrive on sensors, revealing twin ghost images of each hydrogen, proof it occupies two positions at once. That duality allows atoms to shuffle even when temperature forbids, relieving internal stress and preventing brittle fracture. In effect, the glacier glides not only by liquid lubrication but also by subatomic obedience to quantum law. Think of it. A glacier's outer skin may groan and crack at human pace, but inside, time dilates into femtoseconds, letting protons slip inconspicuously across energy lines. Macroscopic drift and microscopic tunneling become expressions of the same imperative. Keep moving, no matter how slow, no matter how cold. Breathe again, this time imagining your inhale as a proton tunneling through the lattice of your own thoughts. Hold, feel possibility on both sides of a barrier. Release and let the proton choose its path. Rivers of ice, rivers of rock. Where basal slip meets regelation, the glacier behaves like twin rivers, one of ice, one of rock and meltwater, braided together down valley. Beneath the frozen mantle, pressurized streams carve winding tunnels called end channels. Their roofs glow sapphire when backlit by sunlight filtering through cracks. Their floors thunder with stone slurry ground as fine as flour. This subglacial plumbing acts as throttle and brake. When channels narrow, pressure rises, friction melts yet more ice, and the glacier surges, advancing meters a day, bending spruces like grass. When channels widen, pressure drops, water drains, regelation locks the bed again, and motion eases to a contemplative creep. Whole surge cycles, months of hush, weeks of gallop, have rewritten river courses in Alaska and Svalbard, carrying entire forests downstream encased in sparkling blue. Every kilometer the ice travels, it scours bedrock with embedded grit, planing granite into kilometer-long striations, leaving roches moutonnées that glint like whale backs after rain. At the tongue, meltwater dumps pyramids of till, shaping kettles, chimes and wandering escorts. When glaciers finally retreat, landscapes appear chiseled by patient giants, U-shaped valleys, string of bead lakes, moraines that trace forgotten margins. On satellite images, these features read like maps of ancient breath. Yet even while sculpting continents, glaciers cradle fragile archives. Each annual snowfall seals a wafer of atmosphere. Dust from Saharan storms, pollen from vanished tundras, ash from Krakatoa, all settle into stratified memory. As the ice flows, layers arc downward, then rise again near the terminus where coring teams retrieve cylinders of time. They read methane trapped during mammoth migrations, lead aerosols from Roman forges, radionuclides from mid-century tests. Without the glide and weld of regelation, those chronologies would fracture beyond repair. Movement paradoxically preserves. Take another breath, in 4, hold 4, out 6, mirroring the glacier's long inhale of snowfall, long exhale of meltwater. Feel shoulders sink like dense basal ice. Feel thoughts slide forward, frictionless. The quiet hero of climate. Modern satellites track glacier velocities to the centimeter, converting pixel shifts into flow maps that warn of fast-thinning ice streams in Greenland and West Antarctica. Changes cascade. As basal water warms, slip accelerates. As surface melt ponds bore moulins to bedrock, regelation cycles intensify. As pressure drops at calving fronts, quantum-steady hydrogen bonds yield faster to ductile creep. The same mechanisms that once built moraines and lakes now sketch uncertainty into sea level forecasts. Still, the physics offers hope. Engineers study regelation to design self-healing concrete where pressure-induced dissolution and reprecipitation close microcracks. Medical researchers mimic ice proton tunneling in polymer electrolytes for solid-state batteries that stay flexible below freezing. Even architecture borrows from glacial kinematics. Deep foundations set onto ice-rich permafrost incorporate slip joints that accommodate slow seasonal flow without shearing beams. A breath like sliding ice. Visualize yourself sliding inside a translucent crevasse. Walls shimmer cerulean. Dust motes suspended in ice sparkle like distant stars. With every inhale, you drift a meter forward. With every exhale, the crevasse gently narrows, supporting your spine. Ahead, light pools at an exit arch framing alpine night. The ice bed murmurs, low, reassuring, as if reciting an ancient lullaby of movement and rest. One last breath. Count 4, hold. 4 and out. 6. Let tension regelate. Melt beneath pressure, refreeze into strength. Glacial motion quiets. Protons settle, night deepens. In the coming moments we will drift beneath the frozen lake where dream and silence converge. But for now, rest upon the slow, steadfast glide of ice sculptors in motion. Dream descent. Under ice eclipse. The glacier's pulse fades to a hush, and the melt cave you drift within darkens to deep indigo. Lie back in imagination and feel the water beneath the ceiling of crystal glass. It cradles you like cool velvet. A slow, lunar glow seeps through snow-blue ice, dimming with every breath you release. Inhale to the rhythm of the frozen river. 4 counts of pure alpine air. Hold, let stillness spread across shoulders. Exhale for 6. Watch ripples travel outward, then vanish into black silk. A single pane of ice overhead grows perfectly clear, revealing a sky of auroral ribbons shimmering green-violet. Their reflections dance on the mirror-calm lake below, blurring the boundary between ceiling and floor until you seem to float between 2 starfields. Your heartbeat slows to match the distant creak of shifting ice. Memory and worry sink like grains of silt, settling into soft layers that will rest for centuries undisturbed. A final breath. Draw it in like moonlight flooding a hidden chamber. Hold glowing within. Release, and the glow settles into calm darkness. You drift farther, weightless, cocooned in cold blue quiet where time itself glides as gently as the glacier above. Nothing more to carry, nothing more to do. Only the vast, serene hush of water at rest. Whisper of crystal and time. Thank you for journeying with night chemistry through water's physical marvels. From its 25 frozen faces and electric ice to gentle density tricks and star-hot bubbles. May these stories rest in your mind like frost flowers on silent glass, shining only when dawn's first light appears. As you slip into sleep, remember, every lake that refuses to freeze solid, every glacier carving marble valleys, every propeller polished bright, all owe their wonder to a molecule willing to bend the rules of matter. Tonight let that quiet ingenuity cradle your dreams, smoothing rough edges, guiding thoughts as steadily as ice flowing to the sea. Sleep well, wanderer of midnight science, and until our next adventure, may your night be clear, your breath be steady, and your rest be as deep as the still water beneath a winter moon.